All right, so we are moving on to finding arc measures. First of all, we need to define what is an arc. An arc is a curve, but it's a segment of a circle. So it's not just any curve, it has to be a constant radius. And just like a circle, it has a center point somewhere. So every point on that arc is equidistant from that center point. So it's easiest to think of it as being a bit of a circle. So it's a little cutout piece of a circle. So it says an arc, and we can measure arcs in a couple of ways. Since it is kind of like a curvy line segment, we could measure its arc length, or we could measure its number of degrees, the angle. So we could also measure its angle. When we say arc measure, we're typically referring to the angle. We're measuring it in degrees or radians as a number of, in an angle measure rather than a length measure. But we will talk about both of these today. So arc measure is a measure of an angle between 2 points on a circle. And it does not have to be in degrees. It could be in degrees or radians, and we'll talk a little today about both of those. Central angle, so you know angles. A central angle of a circle is one whose center point is the vertex of the angle. So this angle here would be a central angle because it begins, or its vertex is the center point of the circle. If we add up all central angles of a circle, so no matter how many wedges we split this into, we can draw a bunch of different radii here, all of our central angles always add up to 360 degrees, as I'm sure you already know. They also would add up to 2 pi radians. So 360 degrees or 2 pi radians are equivalent measures of the total angles in a circle. Then we have the idea of arcs can be divided into minor arc and major arc. So remember when we just did angles. So I did an angle here, and we always define the angle as the included angle between these two rays such that it's less than 180 degrees. So say this was like 30 degrees. I could also measure around this way, and that would be the rest of the degrees, 330 degrees, and we called this a reflex angle. So in terms of our arcs on a circle, we have the exact same idea as that reflex angle, which is if I say arc CF, that means the shorter arc connecting C and F. So this is the shorter of the two options of going from C to F. It doesn't matter whether I name it clockwise or counterclockwise, the minor arc is the shorter distance. And I could write that as arc CF, like that, with a arc over the top, kind of like the way we write line segments. This is the notation for how we write arcs. The measure of a minor arc is always less than 180, just like our angle measures for normal angles that are outside of a circle. And it is equal to the measure of its central angle. So it's saying measuring the arc out here as 40 degrees or the central angle as 40 degrees, they're the same measurement, meaning what that really is getting at is the radius doesn't matter. No matter what radius the circle has, that arc travels 40 degrees. It'll be longer or shorter in measured length based on the radius, but the number of degrees are the same whether I measure it by the center out here or even way out here. It's still 40 degrees. The major arc, on the other hand, goes the other way around. So that would connect C to F this way. But when we say CF, the understanding is that always means the minor arc from C to F. So to name a major arc, we need to bring in another point saying to go around that way. It's kind of like if you've ever used Google Maps or anything like that. It's going to give you the shortest distance from one location to another, but you can set a waypoint somewhere and say, oh, on the way, I need to go by G before I get to F, and it'll reroute it so that you go a longer distance to go by the spot you need to visit. So this is the longer arc connecting two endpoints on a circle. And to name it, we need a third point. So we would call this arc CGF, and with the arc notation again. So if we name an arc by 3 letters, that means it's a major arc and we're going around the long way instead of the short way. It's always between 180 and 360. So again, just the same as this reflex angle. Same exact thing as that. So it is greater than 180 and, oh, it's also equal to 360 minus the minor arc. Just like here we had 30 and 330, or here we have 40, and going around this way we would have 320 degrees. Yeah, so major arc, minor arc should be familiar concepts, just with new names and maybe new notation. A semicircle is an arc that splits the circle exactly in half. So it's an arc with endpoints that are the endpoints of a diameter, and it's always 180 degrees. It's exactly half of the circle. And in any given circle, we can draw infinitely many diameters depending on where the 2 points are. We just have to go through the center. So technically there's infinite ways to divide a circle into 2 semicircles depending on what diameter we choose. Semi, by the way, is just like hemi, so kind of like hemisphere is half of our globe. Semi means half as well, so half of a circle. All right, next we have finding some angle measures. So it says given circle P over here, so center point is P. It says measure of TPU is 25, that should be degrees. Measure of angle SPT is 80 degrees. And PT is 5. So that's important because that gave us our radius. So we know the radius is 5 and the diameter is 10. RT and QS are diameters. Okay, sure, we know that. That's should be able to be assumed from the drawing based on we can assume that's a straight line and that it contains those 3 points. So yeah. All right, so first thing it says QS, that's a diameter, and we just said the diameters are equal to 10 whatever our units are. Measure of angle RPQ, so that's this angle right here, and we know TPU is 25 degrees, and SPT, I'm going to get rid of this 5 since we've already labeled the radius and diameter separately. SPT is 80 degrees. Well, I can see that RPQ is vertical to that one, and vertical angles are still a thing, so that means that's 80 degrees as well. Measure of arc TSR. So 3 letters sounds like I'm going a long way around, so TSR. Well, I went from one end of a diameter to the other, so that means it's 180 degrees. So I formed a semicircle by going from T to R. If I went TUR the other way around, it would have been exactly the same thing. All right, measure of arc US. So US means I'm going from here to here, the shortest distance, so that's around clockwise, which is 25 plus 80. So that's 105 degrees. And I'm adding these together by the arc addition postulate down here. It's exactly the same as you'd think, like segment addition postulate, angle addition postulate. It just says if you have 2 arcs that are next to each other, then you're going to have the sum of their angles, right? So I have 2 adjacent arcs, meaning that they're on the same circle and they share an end point. They share end point T, and they're part of the same circle, so I can add their measures. And then finally we have RSU. So notice they had to name it with 3 letters because we're going more than halfway around the circle to go this direction. If they just said RU, we would be going clockwise, but they're forcing us with this S to go counterclockwise around to U. Let's see what we know about our measurements. We know from R to T is 180, plus we went another 25 from T to U. So 180 plus 25 is 205 degrees. So yeah, that pretty well covers angles of arcs. They're pretty straightforward. And just remember, the idea with angles is it doesn't matter what the radius of the circle is. So any circle, or any arc that goes through the same number of degrees has the same arc measure as far as its angle. What we're going to talk about down here, though, is the lengths of the arcs, I think. So two circles are congruent if they have the same radius. We talked about that in the notes from 10.1 yesterday. Two arcs are congruent if they have the same radius. Nope, same measure. So radius is taken care of by the second part. So if they have the same measure, remember that means angle measure, and they are arcs of either the same circle or two congruent circles. Because if they're on congruent circles, they might as well be the same circle because same measures. So when we're talking about congruent, we're not talking about angle measure. Now we're talking about the length of the arcs. So congruent means two things that are equal in length. So it says, tell whether arcs CD and EF are congruent. Explain why or why not. CD goes from here to here, and EF goes from here to here. They belong to the same circle, so they have the same radius, and they have the same angle measure. That means they are congruent arcs. So yes. Here, CD and EF have the same angle measure because they share this angle. So by the reflexive property, FQE and DQC are the same angle. So they have the same angle measure, but they have different radii. So that means they are not congruent. They can't be because they're on different radii. And then finally, this one we have CD and EF. So let's see, it looks like CRD is vertical to ERF, meaning that we have same angle measures. And these are all part of the same circle, so we have the same radius. So that means they are congruent. So yes. So those are the two things we're checking to see if two arcs are congruent. Do they have the same radius, and do they have the same angle measure? All right, adjacent arcs we talked about above when we were doing the arc addition postulate. It's just two arcs in a circle that have exactly one point in common, meaning wherever one stops, that's where the next one picks up. They share that one end point. Blank is the distance between endpoints along an arc. So this should be arc length, which I mentioned up at the top of the notes. So arc length is measuring an arc not by the number of degrees, but by the actual length of it. So think if you were making it out of like tape or something, how much tape would you need to go around that distance? So it's measured in linear units, like inches, millimeters, and so on. Since an arc is part of a circle, then the arc length is a fraction of the circumference. The ratio of the length of an arc to the circumference is equal to the ratio of the degrees to 360. So we could say something like 120 degrees out of 360 degrees is proportional to the arc length L, so that's that part, the portion, 120 degree portion, over the total circumference, which we said earlier yesterday was 2 pi r. So we have this proportion where we could simplify the left side and make it 1/3. And then cross multiply, we would get 2 pi r equals 3L. And then that's a pi somehow. I know it doesn't look like one. Then r would be 3. No, we want to solve for L in terms of r. Whoops. They didn't give us what r is. Okay. So L is, we're going to divide by 3, and we'll get 2/3 pi r. So it depends on what the radius is, but for this circle where we have 120 degrees, that would be the ratio. Where even did I get the 120 degrees? I have no idea. I must have gotten it from this problem here. Aha, I did. I was thinking ahead, sorry. So now we just did the first part of this problem. We set up the ratio. So this would have been x over 360 equals L over 2 pi r. But since we already did the work of solving this, we can plug in our radius and say that the length of AB is equal to, I guess that would be measure of AB. I need to check that. AB is going to be equal to 2/3 times pi times 15 meters. So that would be 15 over 3 simplifies to 5. So we would get 10 pi meters. All right, so I just went and checked real quick to see if we had notation for arc length, and it doesn't really seem like there is. So we can either say arc length equals that, or it seems like pretty commonly, or most everywhere, S is used as arc length. So I don't really have a right way to put that. So we don't have, like, for angles, you know, we have measure of angle A or whatever, or for segments we have like AB to denote the length or the measurement of that thing. It doesn't seem like there is an equivalent for arcs that I can find easily, at least. So we're just going to say the arc length is 10 pi meters. So remember, pi is about 3.14, so this is about 31.4 meters. If you were going to walk from A to B along this curve, you would have walked about 31.5 meters. Okay, so we can also measure angles in units based on arc length. So I guess we're going to call this the radian measure or angle measure. And we usually in math refer to angle measures by Greek letters like alpha or beta or theta, like this one, or phi. So this one, theta, is kind of our generic angle measurement notation typically, just like x is kind of our generic variable in algebra. So pretty similarly, you'll see theta a lot. So you may have already seen me in trigonometry being like sine theta or tan theta. That's why, is that's just like the name we use for generic angle. So radians are just a different way of measuring angles. They are based on a circle. That's where 2 pi, that radians come from the fact that a circumference is 2 pi r. So we divide the circle into 2 pi radians. Radians are weird. They're a dimensionless or unitless quantity. So like 40 degrees, I don't know the equivalent of 40 degrees. Why did I do 40? 45 degrees has the units degrees, but this is equal to pi over 4 radians, but we don't write radians. We just put pi over 4, and sometimes they'll put rad to note that it's radians, but really radians don't have units in the way that degrees do. So you noticed above we had degrees over degrees and they canceled out. But radians don't really need that because they don't have a unit in the first place. I know that's confusing and not that important for what we're doing, so don't worry too much about that. Just kind of know that radians don't have units. They just are radians. They're just a measure of an angle that doesn't need units. Okay, so we're going to find the length based on this angle measure, which is in radians rather than degrees. So this angle measure is 2 pi over 3. Note that that's the same as 120 degrees, right? That's a third of the circle. But the nice thing about this one is with radians, we don't need that proportion that we had before, because we had to set up a proportion that said our total circumference is 2 pi r. But now the 2 pi is just part of my angle measure already, so I don't need to worry about that. So if I have an angle measured in radians, then instead of setting up a proportion for the arc length, I can just say it's 2 pi over 3 times the radius. And then I'm done. I don't have to do the extra stuff. So let's look back at the one we did, and instead of 120 degrees, let's make this 2 pi over 3 radians. And if we did the same calculation, we would have done 2 pi over 3 times our radius of 15, and we would have gotten 10 pi. Exact same thing, but a little more straightforward. And that's why generally radians are the preferred way of measuring angles once we get past geometry. I'm glad that we get to introduce them here because they are kind of the superior or more established or more expected way of measuring degrees in higher math. So if we want to convert degrees to radians, it's a really simple conversion. If you think about a coordinate plane, if we go from 0 degrees to 180 degrees, so we make an angle that goes from there to there, then we have 90 in the middle. Well, this 180 is the same as pi radians because we've gone half of a circle, and a circle is either 360 degrees or 2 pi radians. So this 180 degrees is the same as pi radians, and that gives us our conversion factor. So if we want to go from degrees to radians, we need to bring in a pi at the top, so we do times pi divided by 180. So for example, if I had 60 degrees and I want to change it to radians, I would do times pi over 180 degrees. That way my degree units are going to cancel out. Those go away. And 60 over 180 is 3, so I just get pi over 3 is the same as 60 degrees. Going the other way, I need to bring in the degree units. So if I had pi over 6 radians, and I wanted to change it to degrees, I flip the conversion factor over so that now I'm ending up with a degree unit in my numerator. And then on bottom, I divide by pi because I need to, I don't need to cancel anything. I just need the degree on top. But it is going to cancel pi here. 180 over 6 means that pi over 6 radians was 30 degrees. Oh, I forgot there were examples here. We can do those too. So 45 degrees. If we're changing from degrees, remember we need to cancel degrees. So that goes on bottom and pi goes on top. And then we cancel our degree units, and 45 over 180 is 1/4, so that's pi over 4. Going the other way, they have 5 pi over 6 radians, and we're going to change that to degrees, and we're going to divide by pi. So whatever we're changing it to, that's the thing that goes on top. Changing to radians, pi goes on top. Changing to degrees, degrees goes on top. Here again, pi cancels out. 180 over 6 is 30. 30 times 5 is 150 degrees. And that's it. So pretty easy to change degrees to radians if you need one or the other. But they are very different, obviously. So like when you are using the calculator, that's why it's so important we make sure it's in the right units. Then today's practice is this worksheet. So there's practice identifying arc measures, both by angles and by length, and then just identifying all the different stuff about arcs that we've talked about today. So do that practice and you'll be good.